Bismillahirrahmanirrahim. In this lecture, I am solving problem 5.4 from the book Applied Thermodynamics by McConkey. The name of the book is Applied Thermodynamics by McConkey. So, the statement of the problem is a closed cycle gas turbine unit operating with a maximum and minimum temperature of 760 degrees centigrade and 20 degrees centigrade has a pressure ratio of 7 by 1. Calculate the ideal cycle efficiency and the work ratio. So first I draw TS diagram for the closed gas turbine, temperature in Kelvin and entropy in kilojoule per kilogram per Kelvin. So there are two constant pressure processes and two constant entropy processes in the closed turbine. So these two are constant pressure processes and these two lines are for constant entropy, isentropic process. So from 1 to 2, this is basically compressor, and we know that there is work input and compressor. From work input in compressor at constant entropy, and from 2 to 3, this is a heater, and heat is supplied as constant volume. 2 to 3 has a heater, in heater heat is supplied at constant pressure. Heat is supplied at constant pressure. Similarly, from 3 to 4 is turbine, and turbine gave us work output. Turbine gave us work output. And from 4 to 1, this is this is cooler, basically cooler, and in cooler heat is rejected at constant pressure. It means that from 2 to 3 is constant pressure process, means P2 is equal to P3, and 1 to 4 or 4 to 1, this is constant pressure process. P4 is equal to P1. P4 and P1 are equal, and P2 and P3 are equal, and the maximum temperature in this cycle is basically T3, and minimum temperature is basically T1, and this is T4, and this temperature is T2. T3 and T1 are given to us, maximum and minimum temperature. A closed cycle gas. Now I can write data with the help of this cycle. So given data, a closed cycle gas turbine unit operating with a maximum and minimum temperature of 760 and 20 degrees centigrade. So maximum temperature is 760 degrees, which is T3. Maximum temperature in this cycle is T3. So T3 is equal to 760 degrees centigrade. Convert this value into Kelvin. So 760 plus 273 Kelvin, which is equal to 1033 Kelvin. And minimum temperature is T1. So T1 is 20 degrees centigrade, which is equal to 20 plus 273 Kelvin, which is equal to 293 Kelvin. T3 and T1 maximum and minimum temperature is given to us. Has a pressure ratio of 7 by 1. 7 by 1 makes 7 is maximum and 1 is minimum. So high pressure is 0.2 at 0.2 and 3, and low pressure is 0.1 and 4. So P2 by P1 or P3 by P4. P2 divided by P1 is equal to P3 divided by P4 is equal to, this is ratio of P2 by P1, high pressure and low pressure, or high pressure and low pressure. And we know that P2 is equal to P3 and P1 is equal to P4. This is 7 by 1. Required is calculate the ideal cycle efficiency and the work ratio. Find ideal cycle efficiency and work ratio. Assumption: assume that working fluid or the working gas is air. Working fluid is air. And second assumption that air is perfect gas. So we will use perfect gas equation. Air is perfect gas. Now we start solution. So for solution, to find work in heat supplied and heat rejected, first we will have to find T2 and T4. T1 minimum temperature and T3 maximum temperature are given to us, but we have to find T2 and T4. So for T2 we know that T2 divided by T1 divided by T1 is equal to P2 divided by P1 gamma minus 1 divided by gamma. Gamma per year is 1.4 per year. So T2 is equal to T1 multiplied by P2 divided by P1 into gamma minus 1 divided by gamma. So this implies that T2 is equal to, the value of T1 is 293 Kelvin. P2 divided by P1 is 7 divided by 1. And the value of gamma is 1.4 minus 1 divided by 1.4. So T2 is equal to 293 Kelvin multiplied by 1.4 minus 1 divided by 1.4. So 1.4 minus 1 is 0.4, and 0.4 divided by 1.4 is equal to 0.2857, and 7 by 1 is equal to 7. So T2 is equal to 293 Kelvin multiplied by 7 power 0.2857 is equal to 1.74359. So this implies that T2 is equal to 510.87 Kelvin. Now we are finding T4. So similarly I can write formula for T4 is T4 divided by T3 is equal to P4 divided by P3 into gamma minus 1 divided by gamma. And here we know that P3 by P4 is 7 by 1, but here it is P4 by P3. As P3 divided by P4 is equal to 7 by 1, so it's reciprocal. P4 by P3 is equal to 1 divided by 7. So T4 is equal to T3 multiplied by P4 by P3. The value of T3 is maximum temperature 1033 Kelvin, which is given to us. P4 by P3 is 1 by 7 into 1.4 minus 1 divided by 1.4. Now solve this value. So T4 is equal to 1033 Kelvin multiplied by 1 divided by 7 is 0.1428 0.2857, and 1.4 minus 1 divided by 1.4 is 0.2857. So T4 is equal to 10, this is 1033 Kelvin, multiply by the 0.142857 power 0.2857 is equal to 0.5735. So T4 is equal to 592.4 Kelvin. Now we can easily find heat supplied and the heater, and heat rejected and the condenser. So Q supplied, heat supplied, is equal to CpN2, heat it's supplied here, T3 minus T2, from 2 to 3, this is heater. Heat is supplied here at constant pressure. So this is equal to Cp. Because pressure is constant, so in formula we will write Cp N2 T3 minus T2. Process from 2 to 3. So it is equal to T3 minus T2. So heat supplied is equal to, the value of Cp per year is 1.005 kilojoule per kilogram per Kelvin. T3 is equal to maximum temperature 1033 Kelvin minus T2 is already 510.87 Kelvin. 510.87 Kelvin. So heat supplied is equal to 1.005 kilojoule per kilogram per Kelvin, multiply by, this is equal to, or simplify this whole value. So this is equal to, this is kilojoule per kilogram per Kelvin, and 1033 minus 510.87 is equal to 522.13. 522.13 Kelvin. So this Kelvin will be cancelled with Kelvin, and finally heat supplied will be equal to 524.74 kilojoule per kilogram, and heat rejected in condenser or in cooler is equal to Cp, because in cooler pressure is constant, therefore we will write Cp. This is cooler or heat rejected at constant pressure from 4 to 1. So we will write this T4 minus T1. Heat rejected is, this is equal to T1 minus T4. Answer will be negative. Negative sign means that it is heat rejected, T1 minus T4. So Q rejected is equal to Cp, value is 1.005 kilojoule per kilogram per Kelvin. T1 is basically minimum temperature 293 Kelvin. T4 is 592.4 Kelvin. So if we calculate this, answer will be negative, but negative sign just means that heat is rejected. Minus 300.897 kilojoule per kilogram. This negative sign mean that heat is rejected. Now we can easily find cycle efficiency. So cycle efficiency is basically ideal cycle efficiency is basically work net divided by heat supplied, but in work net and heat, in this case this is equal to, work net is equal to net heat supplied, Q net. W net is equal to Q net divided by Q supplied. So Q net is basically equal to ideal cycle efficiency, Q net is equal to, this is Q supplied minus Q rejected divided by Q supplied, and we find it in percentage. 100 divided by 100, so divide by 100 is equal to percent. So ideal cycle efficiency is equal to heat supplied. So heat supplied is basically 524.74 minus 300.897 divided by heat supplied is 524.74 multiplied by 100%, which is equal to 42.65%. So ideal cycle efficiency is equal to 42.65%. Now we are finding work ratio. So for work ratio we are finding Q net. Q net is basically W net. W net and Q net are equal in this case. So this is equal to heat supplied minus heat rejected. So W net is equal to 524.7 minus 300.897, which is equal to 223.803 kilojoule per kilogram. This is basically W net. And gross work output and work ratio formula, gross work term is used, gross work output, and gross work output is basically work of expansion or work of turbine, which is equal to Cp, and work of turbine is basically from 3 to 4. This is turbine work output. This is basically gross output. So T4 minus T3 or T3 minus T4. T3 minus T4 answer will be positive, and T4 minus T3 answer will be negative. So negative sign means that this is work of expansion. So I write this T3 minus T4 so that the work is a positive. So gross work output is equal to Cp is 1.003 kilojoule 005 kilojoule per kilogram per Kelvin. T3 is maximum temperature 1033 minus T4 is 594 and unit is Kelvin. Kelvin will be cancelled with Kelvin, and gross work output will be equal to 442.803. Now kilojoule per kilogram. Now we can find work ratio easily. Work ratio is equal to net work divided by gross work output. Gross work output. Net work is equal to 223.803 divided by gross work output is 442.803. Unit in both cases are equal, kilojoule per kg and kilojoule per kg. It will be cancelled with each other. So work ratio is equal to 0.505. So this is the end of the problem, and for more problems and videos please like and subscribe my YouTube channel and share with your friend. Thank you.